This is the final lecture in Chapter 7, Chemical Quantities and Reactions, and it covers sections 7 through 9. Section 7 is mole relationships in chemical equations. But before we get to those, we need to discuss the law of conservation of mass, which I discussed in the previous lecture, but it's critically important for this next little topic here. And the law of conservation of mass, which was given to us by Antoine Lavoisier several hundred years ago when he studied chemical reactions under incredible, strict, meticulous details, says that in any chemical reaction, mass can neither be created nor destroyed. That is, the mass of the products must equal exactly the mass of the reactants. Mass or particles don't just appear out of nowhere, and they don't just disappear into the nowhere. They have to be present at the beginning and the end of the reaction, which is why we must balance our equations. As this example shows here, we have 215.8 grams of silver reacting with 32.1 grams of sulfur. And so we have silver reacting with sulfur to make silver 1 sulfide as a product. And as you can see here, if we add up the reactants, 215.8 plus 32.1, we get 247.9 grams. And if you zoom in closely here, you'll see 247.9 grams. And that's always going to be the case. All reactions, if everything is done in the exact stoichiometrically balanced ratio, as is the case here, you will get the same mass in products that you had for the reactants. Even if it's not stoichiometrically balanced, you'll have stuff that's left over unreacted. Say this reaction had 220 grams of silver, it would still use 215.8 grams of it, and then you'd have 4.2 grams of silver left over. Let's actually do the math behind this to see if it is at all correct. So first of all, we need to look at the molar masses of everything involved in this reaction. We have silver and sulfur. Silver has a molar mass of 179.868, and sulfur has a molar mass of 32.066, and those are both in grams per mole. So the molar mass of silver is 107.868. Molar mass of sulfur is 32.066. So if we assume that the equation appears balanced, then what we need to do is, if we have 215.8 grams of silver, we need to convert that into moles. So that's our mass of silver. All right, so we get that right there. And we're going to take the same equation that we had from before, and the number of moles of silver is going to be equal to the mass of silver divided by the molar mass of silver. And we get 215.8 grams divided by 107.868, and the units are grams per mole. As I showed before, when you do this, you get moles going into the numerator. As a result of that division, you get the number of moles of silver equaling 2.000 0.593318 moles. And we need to round that to 4 significant figures because the first one is 4. So we have 1, 2, 3, 4. And then we look at the next number, which is a 5, making it round up. So we get the number of moles of silver equals 2.001 moles. All right. Now, if that picture here is true, what we need to do here is take those number of moles of silver and convert them to moles of sulfur. So what we notice from the balanced equation is we have 2 atoms of silver for every 1 atom of sulfur, but we can also have 2 moles of silver for every 1 mole of sulfur, because a mole is a number that is gotten by counting. Just like a dozen is 12, we could have 12 eggs or 12 cars. If my, I don't know, let's say my car has a dozen wheels on it and it has 2 dozen hubcap pieces, I don't know, then you could see the same relationship. But so what we do here is we're going to take the 2.001 moles of silver, do the box method, and use this, which is a mole to mole factor or a mole ratio. And we're going to take 1 mole of sulfur divided by 2 moles of silver, and you can see the moles of silver cancel out. But we're then going to multiply by the molar mass of sulfur, which is right there, 32.066 grams of sulfur per mole of sulfur. So now our moles of sulfur cancel out, leaving us with grams of sulfur. And it should come out to 32.1 grams. Well, you can see basically 2 divided by 2 is 1. But when you do the entire calculation, you get 32.0755 grams of sulfur. Now we have 4 significant figures. We have infinitely many. This is 5. Your answer is going to be 4. So we have 1, 2 significant figures, 3, 4. And we look at the 5th. So this actually ends up becoming the mass of sulfur here is 32.08 grams of sulfur, which is essentially the same as 32.1 if you're rounding it to 3 significant figures or to the first decimal place. The balance there only goes to 1 decimal place, so it doesn't necessarily work as well. But 32.08 would technically be the correct answer. The balance in that picture is not good enough to show that level of precision. So as you can see, this one works out exactly as we would expect it. That leads us into these mole-mole factors, and these are based on the ratio of the number of atoms of elements or molecules of molecular compounds or formula units of ionic compounds present in a balanced chemical equation. And they're used to convert the moles of one reacting species to the moles of another. Like in the last example, I had 2 moles of silver atoms for every 1 mole of sulfur atoms. Example 11 here, same basic concept. It says, when acetylene C2H2 burns in oxygen, high temperatures are produced that are used for welding metals. And you can see the equation there. I would always check to make sure it is balanced. You have carbon on the left here. There's 2 carbons in acetylene. There's 2 molecules of acetylene for a total of 4. You can see carbon there. We have one molecule on the right side with carbon. There's only one carbon in CO2 in each molecule, and there's 4 of them. So those are the same. The hydrogens in acetylene, there's 2 hydrogens. 2 times 2 is 4 total. We only have 1 on the right, and there's 2 hydrogen atoms in water, 2 water molecules for a total of 4 hydrogen atoms. And then we have oxygen. 5 times 2 is 10 oxygen atoms on the left. 4 times 2 there is 8, plus 2 times 1 is 10. So everything is balanced. You should always make sure that that is the case. Check for those on every problem. And if it's not balanced, you should balance it. So it says here, how many grams of CO2 are produced when 54.6 grams of acetylene is burned? So if we're especially going from the mass of one species to the mass of another, we will absolutely need to know the molar mass of every molecule that is involved in this question. So that means we need this periodic table. And so what we actually are using here, we have CO2 and acetylene. How many grams of CO2 are made when a certain amount of acetylene is burned? So we need carbon, oxygen, and hydrogen molar masses. Well, the hydrogen is 1.008 grams per mole. And the carbon is 12.011 grams per mole. Oxygen is 15.999 grams per mole. I'll leave that way over there. So what we can do is say we have the molar mass of CO2, and that's going to equal 1 times 12.011 for the carbon, plus 2 times 15.999, and that's for the oxygen. And we get 12.011 plus, and it's 31.998 grams per mole. So we get a molar mass of CO2 equaling 44.009 grams per mole. Now, that had 5 significant figures. 31.998 has 5. This had 5. It still has 5. Now when you're adding, you look at decimal places. We've got 3 to 3, so our number has to have 3, so we leave it like that. All right, the next one we need the molar mass for is acetylene. So the molar mass of C2H2 is equal to 2 times 12.011 plus 2 times 1.008 grams per mole, and we get 24.022 plus 2.016 grams per mole. We get a total of 26.038 grams per mole. Now, looking at significant figures, this had 4, 2.016 has 4, 12.011 has 5, 24.022 has 5. We're adding, so we look at decimals, 3 and 3, so we get 3 there. And that is the molar mass of acetylene. All right, now that we have those, we can use the mass of the acetylene used in the reaction to convert to the mass of carbon dioxide that would be produced. All right, so I can put that there. And so you always start with what quantity that is measured that you're given for these problems, which is the mass of the acetylene. So I'm going to start with 54.6 grams of C2H2. Nothing goes there, it's just a mass of it. And that's going to be multiplied by the reciprocal of the molar mass of acetylene, or we could say it's being divided by it. So we have 1 mole of C2H2 for every 26.038 grams of C2H2. Now comes the mole to mole factor. In the balanced equation, if you see it, we have 2 for the acetylene and 4 for the CO2. So in this, what we want to do, by the way, these cancel out, is always put what you want on the top of the equation or in the numerator. So what we want is ultimately CO2. So the mole ratio is 4 moles of CO2 for every 2 moles of acetylene. And now the moles of acetylene cancel out. We have moles of CO2 there. And now we need to multiply by the molar mass of CO2. So it's 44.009 grams of CO2 per mole of CO2. So you get moles of CO2 canceling out, leaving you with just grams of CO2. Now I want to point out the first stuff here. You're dividing always first. You're multiplying always last. And then the middle portion is always the mole ratio, or the mole to mole factor. I call it the mole ratio. And it's based on the balanced equation. All right, so first of all, doing this step right here, that is going to give us the moles of acetylene based upon the mass of acetylene. By using the mole ratio, we convert the moles of acetylene that are used to how many moles of CO2 should be produced, assuming everything went perfectly. And then once we use that, in the last step, by multiplying by the molar mass of CO2, we get the mass of CO2 that should be produced. And what we get is 184.5680 grams of CO2. Now looking at significant figures, 54.6 has 3. There's infinity for the 1. There's 5 down there. Both of these have infinitely many because it's a conversion factor. We've got 5 and we've got infinity there. And our answer therefore needs to be to 3. So 1, 2, 3. And then our fourth digit is a 5, rounding this up. So the mass of CO2 rounds it up to 185 grams of CO2.